Hello, everybody. Welcome back to ETM 507, the ETM Graduate Seminar. It's my pleasure today to introduce Dr. Bill Dresselhaus. He's currently the Adjunct Assistant Professor in the ETM department and also the President and CEO of the Dresselhaus Group, a product design and design education consultancy. Dr. Dresselhaus was the Joint Invited Professor of Product Design and Design Management at the Hongik University in Seoul, Korea from 2009 to 2016. And Dr. Dresselhaus was one of the early product designers in Silicon Valley. In the 1970s, he was a product designer at Apple Computer, where he managed the product and industrial design of the Apple Lisa computer, a product that was not very successful in the marketplace, but from whose ashes rose the Macintosh, which changed the world. And so in there, along the way, and a few of you may have heard me tell this story, he designed Apple's very first mouse. So Dr. Dresselhaus was manager of product design and later acting director of optomechanical design at Infocus Systems in Oregon, essentially the place that invented the ubiquitous computer display projector. His clients include Apple Computer, Infocus, HP, LG Chemicals, and Sun Microsystems. Dr. Dresselhaus has a PhD in product design engineering from Wuppertal University, mechanical and safety engineering in Germany, as well as 2 master's degrees, one in engineering from Iowa State and the other in product design from Stanford. He has executive industrial design program training from the Art Center College of Design in California. His PhD dissertation was on a project concerning developing a methodology for geometric product form design for high technology product development. He currently consults and teaches internationally for a variety of organizations at the graduate and undergraduate level. In fact, he's teaching a class this quarter for us at PSU as a part of the University Systems Cluster, Design, Thinking, Innovation, and Entrepreneurship. But also he's going to be teaching a graduate level class for us this summer, User-Centered Innovation. And this class is open to all MCEX graduate students that are interested in product design. It can be used towards the graduate certificate in new product development management, as well as the master's program in ETM, and possibly other graduate programs with advisors' approval. So without further ado, please join me in welcoming Dr. Bill Dresselhaus. Thank you.
Thank you, Dr. Anderson. Yeah. It's a great pleasure to be here again. I think this is my 3rd time at this seminar, and so hopefully I'll provide something new. I've titled this talk, The Case for Geometric Physical Product Form, which is really what my thesis was about. And so it's based on, this presentation is based on that thesis that I recently completed at Wuppertal University, all via Zoom and all online. So it was actually a wonderful experience. And so let's see if you like what I have to say. If you're interested in my thesis, it's you can go to BillDresselhaus.com, go to the About tab and pull down to Bill's thesis. The entire table of contents, which I didn't know would happen once I PDF'd it, the entire table of contents became clickable. So you can click on anything in the table of contents and go there, because it's 240 pages long. So where did this all start, this product design thing? Well, for most of my career, which is now getting scary to be over 40 years long, I have always been concerned about the so-called collaboration conflict between industrial design and engineering design, the 2 silo system that is so common in industry today. And one of the things that we learned at Stanford when I went through product design there was that you really we tried, all of us there believed that we could integrate what industrial designers did and what engineers did into product design. And we all pretty much believed that, but we're kind of alone in that whole thing. But we had several people that had done that, and I wanted to do that myself. But it was frankly a struggle because of the two silo system, which is so common. One of the other things that troubled me over the years was the conflict between geometric, what I call geometric design, simple, straightforward geometry, versus organic product form. And I discovered that, at least at industrial design schools and with many industrial designers, they felt that, oh, you need to add curves to a product to make it beautiful and aesthetic. And I thought, I'm not sure that's true, and I'm wondering why they might think that or why that's true. And I didn't actually believe it. So I also started thinking, is it possible then to teach engineers product form, aesthetic product form, and have these engineers become essentially integrated product designers that do both the outside and the inside of products? Well, I was then, from about 2010, 2012 to 2016, given the wonderful, rare opportunity in Korea. I was already teaching there, and I was given the opportunity to teach product design aesthetics and form to undergraduate engineers in the engineering school at Hongik University. And it was a wonderful experience. It took me a few terms to get my course together. I had never taught it before in terms of form design to engineers, and they had never learned it before. But there were many, many engineers at that school, which was considered Korea's top design school, engineers who wanted to be product designers. So it was a very popular course, and the results, as we'll talk about a little bit later, were extraordinary. So before I go further, I'd like to give you an idea of what was the foundation of my thesis, of my actual vision of what is product design. Because I feel it's not necessarily a subdivision of engineering, nor is it really a subdivision of industrial design. This is a long description, and if you have time to read it, you can do that. And frankly, Dr. Anderson, I'll be glad to give you these slides later on. But basically, product designers take a bunch of stuff, all kinds of things that we'll talk about, and they organize it and structure it and architect it and configure it and put it into a marketable and sellable product. It's really more like puzzle. It's more like a puzzle. And there are many aspects to it. And I teach that part of that at ETM in my product design course. But it's really, in my opinion, a unique discipline in itself. It's not really quite engineering design completely. In fact, I don't consider myself what I would say as a hardcore mechanical engineer. I once was a hardcore chemical engineer, but I didn't like it too well. And I'm not really, I would say, a traditional industrial designer. So just to clarify what I'm talking about, every product has all kinds of stuff in it: knobs and speakers and switches and PC boards and displays and lenses and power supplies and all kinds of things that are physical components. And those have to be somehow organized and put together into a product to be able to be marketed and sold. And that's where the puzzle part comes from. But also, the product designer needs to also be able to create a structure, a housing, an enclosure, support for all of those components. And that means at times plastic part design, sheet metal part design. As many of you know, maybe, Apple many years ago, a few years ago, went to CNC machined aluminum for its casework, which was a radical change in direction from plastic cases. And so there's fastening, joining, thermal management, weight, safety, all kinds of things that the product designer must be concerned with, materials, usability. And in a sense, to me, the product designer, as my experience has been, we haven't been always the smartest bunch on the team, but we have been basically the system integrators. We had to deal with electronics, optics, mechanical, purchasing, manufacturing, marketing, sales, just about every silo or corporate entity in the corporation to be able to integrate all of this into a physical product. And so in that sense, we were really acting either officially or unofficially as system integrators. One of the things that I really realized as I did my thesis and my research for my dissertation, I found so many of the best foundational design principles in architecture rather than industrial design or even engineering. And I realized that it's possible, and what I promote in my thesis is that architecture is a better model for product design than either industrial design or engineering, actually, because architects have to do the exterior form and aesthetic design. They do layouts of the interior. They do all kinds of cross-sectional details. They do renderings and CAD modeling. They do mock-ups and models, and they also do very clean and simple line sketching of their designs. Well, that's really what product designers should be doing. They're really, in many ways, product architects. So these are some of the main ideas that I developed and worked on in my research and dissertation. So the basic premise, I kind of started out thinking, well, there's a lot of geometric forms, but what I ended up realizing was, and this came out of some of my research with the books and papers as well, that basically if you look at most geometric form products, they're made up of two elements. Cuboids, rectangular prisms, and right cylinders, and just a couple of good forms with some edge details. And so pretty simple, basic material to start with in terms of forms. And also in terms of things like parting lines and separation points and graphics on a product, there's also radial curves, straight lines, boxes, and circles, and parts thereof. And so I was fascinated by this whole idea of combining those two-dimensional and three-dimensional forms. Plus then radial surfaces rather than complex organic Bezier-generated curves with simple radius corners. And I started looking at the products that I'd seen over the many years from some of the best designers literally in the world that I met and worked with in Silicon Valley. And this started to click into what became my thesis. So this whole idea of configuring all this stuff, multiple components, an internal structure, an external enclosure, and then applying some sort of geometric form design into a product. So I learned very quickly, and we'll talk a little bit more about this, that combining a right cylinder and various shapes and sizes of rectangular prisms gives you plenty of options without adding any kind of organic Bezier curved surfaces to, quote, create beauty. There are many beautiful products out there and many opportunities and options for just using these two simple geometric forms and applying various kinds of simple geometric details. So my thesis research was really 5 parts. I looked at the previous design courses that I taught in Korea. I looked at validating, is geometric form common out there? Does anybody care? I discovered many new principles that were already existing out there, many in architecture. Then I created a geometric form-giving product method, and then I demonstrated it. So the first part was my experimental form design courses, and they truly were experimental in Korea. We started out by trying the traditional industrial design method of sketching your forms first and then modeling. Well, that failed completely. Even though we had I taught also a sketch course for engineers. They learned sketching quite well, but it took an entire 15 weeks of a term to get there. And for the students in the form course, sketching was not good enough. And so we ended up going from this, which the engineers, these are all engineer generated sketches of products. But you'll see that they're probably done on a grid with an underlay. And they did a very good job of this, but creating new product forms in this method just didn't work out. So what we found is that they went to CAD directly and immediately with minimal sketching, and created some beautiful forms that I thought were at least as good or not better than what I saw in the industrial design school at Hongik University. So the outcome was really excellent with engineers who I trained in aesthetic principles and then let them use the tool of choice, the tool that they were most used to, which was CAD modeling. So the second part was validating geometric form. Does anybody care about geometric form, or any top line professionals using it? Is there a lot of geometric form products out there? And so I first did my analysis in the 2019 and 2020 Red Dot Design Award. Now this competition is done by Professor Zeck in Germany, and he started it. It's a for-profit competition. Some people complain about that. I don't care. So he makes money at it. It's a wonderful competition. He puts out these 4 books. They used to be only 1 book. Then he went to 2. Now it's 4 books out there, 50 pounds of paper. It's primarily popular in Europe and Southeast Asia. Not too many Americans are in this competition, but it's loaded with product designs from all over the world. So I analyzed the products visually. There's a photograph of multiple photographs sometimes of all of these products. So I analyzed them visually, went through every single page, every single product in all 4 of the books. And here you see the living book, the doing book, the enjoying book, and the working book, and all the totals. And I analyzed whether or not any product appearing to me was fully and completely geometric. And I didn't even count those that were partially geometric. If they had any organic form, I did not count them. So you can see on the bottom all totals out of all 4 books, the entire competition for that year, that almost half of the products were fully geometric in form. So a second way that I analyzed was, and again, my purpose was not to show any detailed statistical numbers of how many products in the world are geometric and how many are organic. My goal was to simply show that geometric form products were common and done, in this case now, by very prominent designers, industrial designers. So Dieter Rams is probably the most celebrated industrial designer of the 20th century. The center book is by Hartmut Esslinger, the founder of Frog Design and his Apple projects and visual work at Apple. And then an Olivetti book of Olivetti product designs. And so I analyzed those in the same way. And these were the results for these prominent designers of the 20th century. And you can see all totals at the bottom. Pretty much 75 to 80% of their products were purely geometric in form. GPF means geometric product form. So the third part of my thesis work was finding form design principles. So I had some good luck teaching product form to engineers. I found some indication that great designers and great design competition had many geometric product forms. So how would I construct a process to create geometric product form? So I looked at books, papers, articles, films, and a variety of resources in architecture, art, graphics, fashion, industrial design, psychology, etc., on the idea of aesthetics and product form. So one of the things that I learned, which was very interesting, was old design books were better than the new academic papers, especially the industrial design academic papers. And so I found many of these books. So these were the main ones here. The one in the upper left, the blue one in that upper left, the short course in industrial design by Eskil Tialva, who's Danish, was done in 1979. The next one, Engineering Product Design by Kane, was done in 1969. The Del Coates book, Watches Tell More Than Time, all of these are out of print, and I have 2 copies of each, was written 2008, I think. I can't remember the exact date, but anyway, it's out of print for Del Coates, who was a famous educator in industrial design and car designer. I know that some of you are familiar with Krippendorf, the semantic turn about product language, Don Norman. And then there's graphic design, geometric design, Christopher Alexander's synthesis of form. He's an architect. The Art of the Engineer, incredible renderings and designs from engineers at the turn of the century, of the 20th century. Aesthetic sustainability, that person is from a fashion background. Francis Ching, famous architectural teacher, etc. So the center book, the little gray one in the middle, Operative Design, was a real boon to find. I was really stunned to find it, that had these operations that you could apply to geometric forms to make them aesthetically attractive. So most of my work and most of my principles and foundational work came from these books rather than industrial design research papers. So a couple books that were a bit disappointing. The one on the left, which is called Design by Burdick, is an excellent book. Great topics, great writing, really, really super stuff. But he completely left out almost any American design. Apple is not mentioned one time, and he only mentions the McCoys once or twice, and so it's way too Eurocentric, but excellent book for general product design. The thing that I learned that was really new in the Elements of Design, which is a book about Rowena Reed Costello and how she and her husband actually started industrial design education in America, which was very abstract, organic, and based on art. Whereas European design, product design, which I think is frankly superior in its education and approach, is more integrated and based on the Bauhaus, which was architecturally based. I read, I can't remember for sure, but there's at least half a dozen pages. Excuse me, I need to take a drink here. At least a half a dozen pages of references in my thesis, but I found most often, far too often, I thought, in academic industrial design papers that there were many methods, but very little validation. The products they worked on were too simple. They were oriented towards consumer sales. They were styling oriented. They didn't like form follows function, very organic. And they were mostly analytical papers rather than applying methods to doing new products. So that was somewhat disappointing, but I found these wonderful principles in the books. I found also, in general, too many words, too much talk, and not enough show in most of the papers, and even in some of the books. They're just, the Tialva book was one of the few books, the only book that I found where in his last chapter 5, I believe, he actually designs and applies all of the methods that he creates in his book to designing a new product, a totally new product. And so that's pretty rare, actually. So part 4 was taking all of these principles and my experience with the classes and courses and the results from the competition and the famous designers, and creating some kind of geometric form method for product design, especially targeted to engineers, and CAD modeling in geometric form. So this was the chart on the left is my, actually it's a simplified chart of what's in my thesis of the steps of going through. But the even more simplified one on the slide is first you find a need, absolutely a human need, and then you define those parameters. You determine what function that need requires and what components and means, functional means. You make sure you've covered all the stakeholders and issues in a product, whether it's safety or repair or sustainability, usability, whatever, not just the user. You make sure you have optimum usability and ergonomics. And once you've done most of that, it's that point that you define the external form design. Form design is almost last, not first. Just to give you a quick story, I have a good friend of mine, colleague who used to work for me, is now down with a engineering company in the Silicon Valley. And he was relating to me recently that he had a client come in. They had a client come in that needed some very sophisticated engineering for their new product. But they also brought in renderings that they had gotten from an industrial design firm that they engaged. And they said, well, can you kind of please make it look like this, because we've already marketed some of these concepts. Total disaster. That's not the way to do it. You don't go out and have people who don't know what the engineering aspects are, what the issues are, and have them design renderings and sketches and concepts for a product before you really delve into all of these issues that I've just mentioned. And so we were kind of laughing at that because, frankly, that's an unfortunate, very common process. To have industrial design kind of overdo it with lots of sketching in the beginning, and then turn that over to the engineers to try and have them make it work. So first you do all the components, all the stakeholders, not dozens of illustrative form concept sketches first. You need to do this. I've done this many times in projects where industrial designers were doing sketches of the concept of products. And I said, well, let's first make a mock-up of everything that has to go into this product and lay it out on the table. And I've done that many times, and everything changes at that point. So part 5 was demonstrating my geometric method to see if it actually worked. Profuse visualization using a minimal sketching process, maximizing 3D CAD modeling, and exploring and even parametrics. So this was a diagram I used in the thesis, and that is in my book on LISA, but here are 13 different parameters that we had to make LISA fit into. It wasn't just the overall aesthetic. We had a stowable keyboard, it had to sit on your lap. There was a 30-inch depth of a desktop. You had a wall in the back. So these are identified in a lot of text in the thesis, but this is the kind of thing that every product needs to be considering. It isn't just the aesthetics and the form and what makes it look good. So for some reason, we're not moving on. There we go. So I wanted to, because of my complaint about too much talk and not enough demonstration and visualization, I wanted to have a thesis that had plenty of visualization so everyone understood my principles and my methods. So there are over 400 CAD models of varying details and features that I produced in my thesis visually. So these are the kinds of things that I demonstrated in my thesis. I deconstructed several red dot products that were selected as purely geometric design forms, and I recreated them visually in 3D CAD modeling to show what their components are. And the program I use, which is Fusion 360, has this wonderful little button that you can click, and it turns every component, every separate geometric form component into a different color. So you can see all the different parts. So that was the idea, to show the configuration of geometric form in all of these products that you see on the left-hand side of that first set of images that were in the red dot competition. In the center section, I demonstrated geometric form proportions. One of the studies that I did was of phi, the so-called golden mean or golden section, 1.618, which is almost almost a magic number. So how, and then I discovered other architectural books that had more derivatives of phi, or 1.618, fractions of it. And so I demonstrated that in several CAD models and showing the proportions. And then on the right, you see geometric form hierarchy. One of the good things that I learned from the Hannah Costello book was the hierarchy of forms, primary, secondary, tertiary, and then quaternary forms, which I added quaternary forms, which are basically small details. So the idea there was you can have one form, two forms, or three forms, and generally better not to have more than that. So that was a hierarchy of forms that I demonstrated. On the left is the one single form operation of rotate. So you can see on the left, there's two forms intersecting, and then on the right, one of the forms is rotated and move slightly as well. So that's what came out of the one architectural form book of many different ways of integrating and intersecting and doing different form operations. In the center, there's product interaction areas. This is one that I learned from Tialva, the so-called interaction areas that need to be clear. And the red areas on that camera are the places where human beings touch the product. So they need to be tactile, and you need to identify what those areas are. And then on the right, functional transformations versus functional means, technology system, and then how to diagram what your product does. And then I gave various configurations of different kinds of products with different components where the functional transformation was exactly the same, but the product was totally different in terms of its components. And then on the left, I showed the transition of how to do orthographic sketching. This is what we had most of our students do in the engineering course, was to sketch in orthographics their concepts for their product, but then both to make models and CAD mock-ups of the various configurations. So in that left-hand set of images, you see two different configurations for a digital projector. And then the second line, second two images, you see two actual real mock-ups that were made in block form of those configurations. And then finally, the two CAD models. And then, of course, some people like to call it, we would skin those components to make the outside enclosure with certain geometric forms. In the center is an example of the development of various variations of forms and applications and color and shifting and operations for a simple laboratory scale. So you can see how it would transition from two simple rectangular blocks and applying those operations, and then adding color and value and different edge radii and details. And then on the right, you see, again, various kinds of controls, push buttons, levers, knobs, sliders, switches, displays. Again, the whole idea behind this is that there's no need whatsoever, in my opinion, and that's what this thesis is all about. There's no need whatsoever to add curves, organic curves to a product at all. There's plenty of variation that can be done with simple geometric forms, whether it's to the detail controls, whether it's the edge radii, whether it's the gross major forms of the product, but using simple geometric forms is just all that's needed. And then I looked at, again, these are just samples of what I did. There's many more of these. Form value variation. So I didn't do a lot of color work. I didn't want to get into that. Color is a very complex subject to colorize your products. So in the set of images on the left-hand side is one or two forms of digital projectors, and what happens when you simply vary the value, dark to light, and you change that in various ways and various elements of the geometric form, and how it changes the appearance, changes it from light looking to dark looking, the various aspects, and how that is perceived by human beings. In the center one is form variation. Another topic that I learned from Tialva is first you put together, like in the first set of images up there, you put together your three basic forms, primary, secondary, and tertiary. Then you start adding large radial surfaces and details in various ways, and then you add edge details and various refinements. So you have to be very careful. One of the principles that I learned and developed in the thesis was don't do too much. Be very careful of adding too much detail, too much variations, too many operations. Keep it simple. And then in the last one, some actual product forms that my own firm had developed in the past. I applied this whole geometric process to it and showed how we developed the geometric forms of the products that were very successful in the marketplace to show how the various geometric elements were applied and how they related to the actual real product. Those are real photographs of actual products that we developed, and I did several of these in the thesis. So in the end, my method had these 7 at least key points: exclusive use of just simple geometric forms and simple proportions, many of them based on the golden section. I did target engineering as to be these product designers. One of the things that happened after I developed the courses and the program at Hongik University, that led into them developing a so-called design-ear program where they did an integrated program for doing industrial design and product engineering together with engineers. I also targeted in my thesis what I call UTPs, utilitarian technology products. This would be like medical products, laboratory products, technical tools, things of that sort. It was very frustrating that when I read some of the industrial design papers, research papers, they would analyze how their students would create different forms for, believe it or not, a fruit bowl. And I thought, okay, so really a fruit bowl? Are you kidding me? One of the lead product design schools in the country, their headline header in their opening website doesn't have some complex product, medical product or sports product, but they have a set of ceramic cups. And so it was really kind of frustrating that I didn't see too many educational institutions or industrial design research papers really tackle very, very complicated products. I mean, and one of the things I did somewhat in my thesis was promote the idea that the world needs complex products designed that help people, that serve people, beyond fruit bowls and ceramic cups. I mean, I'm not demeaning that those aren't necessary maybe for daily life, but we need some dialysis machines and things that are really critical to life and to helping people. And they need great function, great usability, and beauty. So my method also does not require any sophisticated sketching beyond orthographic sketching of forms, and directly goes into CAD modeling as the primary medium of developing. And with the wonderful CAD modelers we have today, I used exclusively Fusion 360, which you can push, pull, and shape things on the fly. And I'm sure most SolidWorks is used at Portland State, and other universities use NX. And they're just incredibly powerful tools to create beautiful products. And my method starts with architecture and configuration of the components first. How do you arrange and order things for optimum usability and functionality before you design the exterior shape and form? And then finally, that architecture should be the model for product design rather than, say, industrial design or engineering design. Architects are total designers. So here's a list of future work that I proposed in my thesis. Actually, a lot of this pretty exciting to do. I'd really like to do a full-blown catalog of geometric forms and possibilities, and how geometric form can be used in various situations. Krippendorf, in his book, The Semantic Turn, talks about the meaning of forms. And he has an example that I repeated in my thesis where he takes just some abstract forms, blocks, cubes, rectangular prisms, and cylinders, and the same ones, and he rearranges them into three different configurations. One looks like an espresso machine, the other one looks like a microscope, and the other one looks like some lab instrument. And they're all the same forms. And so he talks about the semantic meaning of forms, that when Don Norman talks about the idea that you should be able to look at a product and understand what it is, ideally the first time you see it and how to use it. Or the worst case should be you have to have a demonstration or look at the manual or have someone show you how to use it one time. And after that, it is now so clear that every time you approach that product, you know what it is and how to use it. So I also would be fascinated. There was no research that I found that validated whether or not human beings prefer geometric or organic products. There's a lot of assumptions out there by a lot of people, and I'm just not convinced that what some industrial designers feel that you must have organics to be attractive. I just think that is not true, but someone needs to validate that in a real research experiment. So that's pretty much the end. We're at 4:06 here. We still have a little bit of time for some Q&A. Any questions or challenges, complaints, critiques, or comments of what I've talked about here. I do have another slideshow in the background with that's my entire course, part of my entire course on product form aesthetics, if you want to see what I mean by organic or geometric products. So that's it, Dr. Anderson. There you go.
Great. Wonderful. Thank you. Thanks again. We have some questions in the chat. Thanks again for a great presentation. So we can take these straight from the chat. So Pavitra was asking, are these rendered CAD models? I'm not sure at what point that question was asked. It might have been perhaps from the Lisa diagram or another.
Yeah, most of the models I did not render because it wasn't necessary. In fact, in the program I use, Fusion 360, when you do your CAD model, you can select outlines for the forms. And that was important to be able to see the forms rather than render them. So sometimes if you render a form, you can't see the forms as clearly as when there's outlines. So I did render some of the products in there, and rendering is an art in itself. It's not just doing the model. It's all about lighting. It's all about lighting. And I've had students who did just incredible renderings in my Korean engineering students. They were just amazing, stuff I couldn't do yet.
Great. Pavitra, did you have a follow-up question on that? I saw you just joined in.
No, Professor. I figured it wasn't rendered. Few of them weren't rendered, but then because of the finish that it had and the aesthetics that it had, I was just curious if they were rendered image or just the 3D models.
Most of them, as you see in, you just saw in my images, are straight. They're screenshots, a special screenshot method they have in Fusion 360 that eliminates the background and the grid, and it gives you a screenshot, but it gives you the outlines of the various form components, which makes it easy to see what those forms are rather than trying to adjust the lighting. So it's tough.
Yeah, thank you. Thank you for that answer.
Yep.
Yeah.
Great. Dr. Weber. Did you had a couple of questions in the chat.
Yeah, the first one, wait, can you hear me first of all?
Yeah,
Yeah,
I can hear you
okay,
great.
yeah.
Hi,
Yeah,
hi, Dr. Weber.
So your approach to postponing form design reminds me of computer hacking versus software engineering, right? Some people just want to go in and, I need to code right now. And then in the end, they run into cascading catastrophes, right? So
Yeah.
I sort of saw an analogy there. I wanted to hear your comments on that. Yeah.
Yeah, well, it depends. Listen, when I was in Silicon Valley and up here in Portland too, when I was consulting, I've worked with some of the best industrial designers literally in the world. I mean, Hartmut Esslinger, Mike Nuttall, been associated, not work with, but Bill Mogridge, and then reviewing Dieter Rams, et cetera. And so in those cases, those mostly guys, did just a great job of working with engineering. But it's way too common for clients who are doing startups. They go and they hire an industrial design firm, and generally not with a big budget. So they sometimes hire students, and they work hard and they're diligent students, but they're working without a lot of STEM knowledge, and create a lot of what might be really cool renderings and sketches and drawings. But then when it's turned over to engineering, which I've had this happen many, many times to me and seen it happen other places, is that they haven't considered materials, components, sizes, usability, etc. It's just a pretty picture. And so there's kind of two ends. The folks, I'm sure it's in software, there's folks that do excellent software design and code development, and then there's others that jump in and don't know what they're doing.
Okay. Now, my second set of questions was, you mentioned the golden section was magic. And I've been wondering for 50 years, what is magic about the golden section, right? On the one hand, it's a social construction by the ancient Greeks, Parthenon, etc. On the other hand, it's the limit of the Fibonacci series. So there are lots of Fibonacci combinations in nature.
Yeah.
So I don't know. I've been wondering about this for 50 years.
Well, yeah, I agree. It's interesting. I found one book and actually an app that uses Phi, and in this book they have many images where they overlay the golden section proportions in boxes, and they overlay it on the products, and it's just amazing how many places it shows up. Plus the fact it's the limit of the Fibonacci's. It also, I think, if you divide 1.618 by I can't remember the division thing, but it kind of equals itself or the reverse of itself. And so that's the magic part to me. I studied a lot for this thing, for this thesis, and a lot of controversy over it. I found some designers who thought it was absolutely ridiculous and silly to apply the golden section, and then I found others who were rabidly defending it. So it was very interesting.
So, you could argue, for example, the shape of galaxies tend to be logarithmic spirals, which is the golden section. So maybe there is something literally cosmic about it that we're not aware of.
Yeah, it's true. It's really, that's why I say it's kind of magic or mythical or whatever term you might use, but it is mathematically very interesting.
Let's we have time for one more question. So I don't see any others in the chat. So
I see the last one. This is an important thing. Wouldn't adding organic radius and curves help in better stress distribution and product? Yeah, good point. Obviously, if you look at car design, for the sheet metal design, you want curves in it, so you can't compress the, you have structural integrity. My point is, you don't need organic Bezier-driven curves. You can do most of what you want with a radial curve, and that's the difference. I'm not talking about always flat surfaces. If you want a curved surface, it can be a radius, a big radius. If you need that structural integrity.
Great.
In fact, one of the recommendations I did for the thesis for more research is to take a number of products that are perceptually organic and see if you can turn them into a geometric product using only radial curves and flat surfaces, and then see if anybody cares the difference. Because one thing that I present in there, and I believe I'm right on, is that geometric surfaces and forms are much easier to understand than most Bezier curves are arbitrary. I mean, dimensioning them is almost impossible.
Well, so we're running out of time. I wanted to give one last chance if you wanted to talk about your summer class, User-Centered Innovation, and give a little pitch as to what that'll be about.
Yeah, I started teaching this a couple years ago, and as it evolved, I discovered the work of Liz Sanders. I've seen her speak and talk, and actually she ended up in my first book in 2000. I didn't even know that it was her work, but her book, which is Convivial something, I can't remember the whole title. It's a textbook for the course. It's user-centered design, and what I have gone the next step for is that what usually people think of user-centered design is that you're the designer and you design it for the user. That's user-centered. Well, the next step beyond that is having the users actually design the product themselves. Now, they can only go so far with that, but the whole basis of the course is that you become the design facilitator, and you facilitate people who have a stake in the product to design the features and, to some extent, the form themselves. How do you get that input? It's a real challenge. And in fact, the biggest challenge for the course in the past summers has been getting the students to wrap their head around, I want to design this. No. You let your clients and customers design it. And then you may have to put it together in a professional manner, but they design and define what the product is. And that's really what the course is about. And there'll be a term project to do that.
And it sounds like something that's useful for engineers from all different disciplines, not just a mechanical engineer or a civil engineer, but you have a chemical engineering background originally and went into design very successfully. So great. Okay, with that, I'd like to thank you, Dr. Dresselhaus, for today's great seminar, and thank the audience.